everyone to this week's Landscapes Live. I'm very excited to introduce our speaker, Apolline Mariotti. She holds a PhD in Earth Sciences from Université de Lorraine and is currently a postdoctoral researcher at Trinity College Dublin. She's previously held postdocs at the GFZ in Potsdam, the Université de Lorraine, and University College Dublin. Her research is focused on constraining denudation rates and glacier dynamics in different environments using a variety of techniques, including cosmogenic nuclides, thermochronology, and short-lived isotopes. Today, she'll be sharing her work exploring how glaciations impact mountain evolution over both short and long timescales. So with that, I will go ahead and hand it over to Apolline. We will open up the chat for questions about 5 minutes before the end of the talk. So yeah, go ahead and hold on to your questions and Apolline, I'll have you start. Thank you so much for being here.
All right. Thank you, everyone. My name is Apolline Mariotti, and so yeah, I'm a postdoc at Trinity College Dublin. And first, I want to thank the Landscape Live team for organizing this seminar series and for inviting me. And I also want to acknowledge the many collaborators involved in the work I'm presenting today across multiple projects, multiple universities, and multiple labs. So today I'm going to be talking about the impact of glaciation on the evolution of mountain ranges, both over the short timescale, so 1,000 years timescale, and the longer timescale of a few million years. So my research broadly focuses on how landscapes evolve over time, and landscapes are affected by three different forcing. So we have the tectonic forcing, the climate forcing, and the denudation or surface processes. And these forcings also interact with each other to shape the landscape that we know. And today I'll be focusing on one very specific interaction, which is the impact of climate on denudation and through denudation on the topography that can evolve over time. And one aspect of climate that is still a little bit debated is what is the role of glacier and glaciation on the evolution of mountain ranges. And there are basically two different views in the literature. First, we know that glacier can be very efficient for shaping the topography. So for example, here we have a V-shaped fluvial valley being incised by a glacier to become a U-shaped glacial valley. We also know that in some places we have what we call the buzzsaw effect, which is basically above a certain height, glaciers become really efficient at eroding, and through this mechanism, they can prevent mountains from growing above a certain threshold, roughly around 6 kilometers. And so those two mechanisms can show glacier as really efficient in eroding landscape. But we also know that that's not always the case. And glacier can also protect the topography, the underlying topography. So this is a recent study that looked at the glacial erosion rate underneath the British ice sheet. And what we can see for Scotland, for example, is that the glacial erosion rate underneath the ice was much lower than what it is, for example, today. And this is not only true for a big ice sheet. This is also true for some alpine glacier. So this is an example from a study in South Patagonia, where Thompson and colleague went to look for the buzzsaw effect. And so they went to South Patagonia, where we have a strong glacial topography, and they sampled the rocks as an elevation profile. And the assumption was, as you go up, you would find younger rocks because any older rocks would have been eroded away by the buzzsaw effect. And what they found is actually the complete opposite. As they went up in elevation, they found really old rocks. And their interpretation was, in some cases, those old rocks have been protected by underneath the ice in the underneath the alpine glacier. So the key question still remains, which is how much do glaciers reshape mountains? when do they reshape mountains and where do they reshape mountains. And this is still relevant because the impact of glacier and glaciation is variable in time and space. And that is mainly due to the different thermal regime that the glacier can have. So cold base ice will not erode and warm base ice will erode. So just thinking that glaciation means higher denudation rate is not always true. The time period I will be focusing is the Pliocene-Pleistocene. So the Pleistocene is characterized by the onset of global cooling, but it's not a stable period at all. There is a series of glacial and interglacial period in the Pleistocene. And one of the questions I will try to answer is what is the impact of Pleistocene cooling and subsequent glaciation on the erosion of mountain ranges? The first timescale I will be looking at is the shorter timescale, so the glacial interglacial cycles, and to try to constrain the impact of those climatic forcing on the topography, we need to use a proxy that has an integration time that is short enough to detect changes at the 1,000-year timescale. And so if we look at the most common proxy, the one that is quite appropriate here is in-situ cosmogenic nuclides, and more precisely, beryllium-10. In-situ beryllium-10 is a cosmogenic isotope produced by the interaction of cosmic rays with rocks at the surface of the Earth or near the surface of the Earth. So more precisely, beryllium-10 is produced in quartz, and it's produced in quartz within the first 2 meters of the surface. And underneath those first few meters, the rock is sufficiently shielded by the rock that are on top of it so that the production rates decrease very, very quickly. Beryllium-10 is also a radioactive isotope with a half-life of 1.4 million years. And the production rate at the surface will constrain the speed at which beryllium-10 gets accumulated in the rocks. So how do we go from here to constrain the denudation rate with beryllium-10? Well, let's take the example of 2 hill slopes. So we have the hill slope on the left will be slowly eroding. The hill slope on the right has a fast erosion or denudation. So if we start with quartz grains who are deep enough in the regolith to be shielded from cosmic rays, so they start with 0 concentration of beryllium-10. And if we start the denudation process, so the hill slope will lower at whatever speed they are eroding. And what we can see here is that the fast denudation hill slope will produce quartz grain with a lower concentration than the slow denudation hill slope. So we have a really nice inverse relationship between the denudation rate and the resulting beryllium-10 concentration. Now, when we use beryllium-10 for denudation rate, we work at the catchment scale. So of course, we work under the assumption that there is a constant erosion of bedrock that produce quartz grain. And of course, every part of the catchment is going to be eroding at different speed, but it doesn't really matter because the product of this erosion is going to be the sediment and the quartz grain who are entering the fluvial and the river system. And so those sediment gets mixed, and if they are well mixed, then we can sample the outlet of the catchment, and the concentration that we measure in those quartz grain will be representative of the average the average denudation of the whole catchment. So we can do that in modern sand. So any rivers that has quartz you can get the denudation rate. You can also do that in sediment archive, and I will be presenting one very soon. So we studied the Var catchment in the southern French Alps. So the Var catchment is it's roughly 3,000 square kilometers. It's at the foothill of the Alps. So the upstream catchment is really mountainous. The downstream is more of a sedimentary cover. and it is classified as a reactive sedimentary system because it has a very steep mean slope, and there is not a lot of storage space for sediment. We don't have a big alluvial plain. It's quite steep, and which means that most of the sediment, or the sediment that gets eroded on land, gets transported downstream, and ultimately the sedimentary system is connected to a submarine sedimentary system in the Mediterranean Sea, and we have a big sedimentary accumulation over here. And on this accumulation were collected two sediment core. And so those two sediment core, as you can see here, 01 and 13, were collected roughly 200 meters below sea level, and they were collected on the top of the sedimentary ridge. What we can also see here is that we have a nice layer deposition by the seismic data. We don't have big perturbation in the layers. And this is a scan of one of the sediment core. We can also see that we have very nice turbidite deposits, which are characterized by a sandy layer at the bottom. And this is this sandy layer that we use for the beryllium-10. So before going to the beryllium-10, let's talk about what else is available in those two sediment cores. So those sediment cores were studied before by a few people, and they benefit from a very high resolution age model. So we have a lot of C14 constraint points, as well as a lot of oxygen data. And what we see, and that is quite remarkable here, is that the oxygen data matches very well with the NGRIP Greenland data. So we have a paleoclimatic signal that is really well constrained, and that is local to the sediment core. One thing that we looked at before going to the beryllium-10 is the sediment provenance. It's quite important to understand where the sediment is coming from, because in the VAR, there is no glacier at the present day, but there used to be glacier during the LGM, and mostly in the orange and red part. The yellow part didn't have any glacier. So to really understand the denudation signal, we also need to understand where the signal is coming from. And so what we can see is that we do have a lot of noise in the data, but during the LGM, we have quite a stable neodymium, epsilon neodymium signal. We have a very strong change in source right at the deglaciation. We have potential sediment outwash around 10,000 years, but overall, the Holocene signal is very different from the LGM signal. And the Bono and colleague calculated the change in sediment provenance, so between the LGM and the Holocene, and they determined that 40% of sediment during the LGM were coming from the glaciated part of the catchment, versus nowadays it's only 16% of the sediment coming from those previously glaciated part. So that tells us that there is potentially a strong glacial signal during the LGM. It doesn't tell us exactly how fast the glacier were eroding, but we do have a signal coming from the glacier. So this is the beryllium-10 data set that we have. So we have 48 samples, and looking at the concentration, we can see two linear trend. We can see a decreasing trend from 75 to 20,000 years ago, and then an increase in concentration from 20 towards the present day. So how do we go from this concentration to the denudation rate? So we'll use this equation here. So the concentration are here, but we need to talk about P, which is the production rate, and the production rate can vary over time. So for each sample, you need to constrain the production rate associated to this sample. And the way the production rate can vary over time in the VAR is due to the ice. So I'm going to show you a simple cartoon that explains how production rate can be affected by glacier. So if we have here, it's a fluvial valley. We don't have any glacier. every quartz-bearing rocks can accumulate barium-10. Now, if the climate gets cooler and we have a glacier in the valley, then the underlying rocks underneath the glacier are shielded from the barium-10. So the overall production will change. The overall production rate will change. And constraining this change in production rate over time is a little bit tricky. And to try to not overcorrect, what we did is we used two end members. So the first end member consider no impact of glaciation on the production rate. So we know it's technically not true, but that gives us an upper bound on our denudation rate. The second end member is probably the one closer to the reality. And we corrected each production for each sample, we corrected the associated production rate using glacial extent that we modeled with the local oxygen data. So the oxygen data from the core were used to model the associated ice extent. Here we have the denudation rate for the first ice member, so end member, sorry. So the end member that doesn't consider any ice. What we see is we have in gray, we have the variability of the present day denudation rate in the VAR. And we see that the denudation rate from 75 to 30,000 years are quite stable and quite similar to present day denudation rate. We have a big spike of denudation rate during the LGM, and then denudation rate are going down during the Holocene back to present day level. And now looking at the second end member, so we see that the results are very, very similar. So stable denudation rate during MIS 5, 4, and 3, increase of denudation during the LGM, and then denudation going back down during the Holocene. And so what is quite interesting here is that the spike of denudation rate correlates very well with the LGM. And thinking about it, we felt, okay, so the LGM is the biggest ice extent, the biggest ice extent. So if this increase of denudation rate is due to an increase of glacial erosion rate, by how much glacial erosion rate need to increase to reproduce the spike that we see here? To do that, we used a very simple mixing model. So it's very simplistic, but I think it works quite well. And we considered that the sediment in the VAR catchment is produced in two different ways. So we have in green what we will call the fluvial component. So it's not strictly fluvial, it can be periglacial as well. But let's say it's any sediment that is not coming from underneath the glacier. So anything that's not strictly glacial will be considered as fluvial. And those fluvial sediment have a set denudation rate. And we also have the second source of sediment that is coming from underneath the ice, so the glacial component. And this glacial component will be characterized by a barium-10 concentration that is either it is very low or that can be zero. And so those two types of sediment are mixing in the fluvial system. And so in the end, when we measure them in the sediment core in the sea, well, we actually measure the dilution of the fluvial concentration by the glacial component of the system. And so the idea is that if you can fix all the parameters, except for the sediment flux coming from the glacier, then you can deduct the sediment flux coming from the glacier. And so the way we did that is because the denudation rates are relatively stable over MIS 4 and MIS 3, we basically took the average of those values, and we used it to calculate the average glacial erosion rate over this whole period. So for MIS 3, MIS 4, we have a glacial erosion rate around 0.4 millimeter per year. During the LGM, it's much higher, it's 1.5 millimeter per year. So it does seem to indicate that we can explain the spike of the denudation rate during the LGM purely by an increase of glacial erosion rate. So now we can ask, okay, so why would the glacial erosion rate be that much higher during the LGM? Well, Herman and collaborator in 2015 looked at a glacier in New Zealand, and they really show really nicely that the erosion rate of the glacier is a function of the ice velocity. So what we did is we compared the ice flow during MIS3, MIS4, and the LGM. And what we see is the LGM, sorry, is associated with much thicker ice, and that results in much faster ice velocity compared to the MIS3. So we do have a mechanism that would explain why we have a fast glacial erosion rate during the LGM. So here's the best summary of this project. This is a plot of the denudation rate on the left versus the local oxygen data. So again, this data is the local oxygen data measured in the sediment core, and it's basically a proxy of the local climate. And what we see here is that the relationship between climate and denudation is relatively stable over a wide range of oxygen data, except for when a threshold is crossed. And this is where the denudation rate can go much higher, but not necessarily have to go higher. So we do have a nonlinear forcing of climate on mountain denudation during the very recent glaciation in the VAR. Okay, great. So what about the impact of glaciation as a whole on the landscape? What's the impact of the cumulative glaciation on the landscape? So to answer this, we have to change proxy because we want to integrate a signal that is over a longer time period. And to do this, we'll be using low temperature thermochronology, and I will be focusing on apatite helium thorium system. So low temperature thermochronology records rock cooling. So there's a lot of different systems, and each system has a sensitivity that is going to be determined by the closure temperature. So below which you can record the age. So I'll be focusing on the apatite helium system and the apatite fission track system. Apatite helium age is based on the temperature-dependent diffusion of helium atoms that are produced by the radioactive decay of uranium, thorium, and samarium in the apatite crystal. So basically, when the crystal is hot enough, any helium that gets produced by radioactive decay will diffuse out of the crystal. And when the rocks cools down, the sample cools down, any helium that gets produced will then gets retained. And so past what we call the closure temperature, we can start recording time. And this is this is calculated when we measure the concentration of helium, uranium, thorium, samarium in the crystal. So there's two dynamics that can affect rock cooling. The first one is going to be the movement of rocks relative to the surface, so the rock uplift. And so that's going to be thought as a tectonic forcing. The other mechanism that can also affect rock cooling is going the other way. So that's the movement of the surface relative to the rocks. So that's going to be, for example, valley incision or valley widening. So for example, in this cartoon, we go from a V-shaped fluvial valley to a U-shaped glacial valley. And this is going to be thought about as a climatic forcing. And it's quite critical to account for the topography changes when we interpret cooling ages, because in this case, for example, valley incision can bring to the surface younger samples that were possible in the fluvial valley. So we use this method in the Tian Shan. So the Tian Shan is located in Central Asia. It is quite a big mountain range that covers thousands of kilometers. And for the first study I'm going to be presenting today, I'm going to be going to the Kyrgyz range, which is the northern extension of the Tian Shan. So the Kyrgyz range, which is here, spans about 300 kilometers. And it's bordered to the north by the Chu Basin, which is a big sedimentary accumulation. And specifically in the Kyrgyz Range, I will be looking at the Ala-Archa Valley. So the Ala-Archa Valley present a very strong glacial morphology. You have here a drone picture of the Ala-Archa Glacier, and topography analysis by Oskin and Burbank showed that we can have between 0.4 to 1 kilometer of glacial incision in really nice about working in the Kyrgyz Range is that previous thermochronology studies have used apartheid fission track to constrain really well the background tectonic signal. And so this is landscape evolution model that's been published in 2006 by Sobol and a colleague, where they constrained the start of the exhumation of the range at 11 million years ago, then a slowing down of the exhumation between 10 and 2 million years, and then exhumation picks up again around 1 million years. And so what we did is we went exactly, well, not exactly, but we went in the same valley where they sampled the fission track. And we basically resampled almost exactly where they went for helium ages, which have a lower temperature sensitivity. And so we did an elevation profile, and the idea is that as you go up, you sample all the rocks, and you can go back in time by going increasing elevation. So we have 7 new apatite helium sample who are yielding very young ages, so between 3.2 million years up to 7.4 million years. And so we also sampled the main valley as well as the glaciated trunk. And the first thing we did is we looked at a 2D model called QTQT, and what this does is working with the grain chemistry and the grain parameters, you can invert for the common cooling history for all samples. So this is what the cooling history for the whole profile tells us. So we have cooling between 30 to 13 million years ago. We have the onset of exhumation that was seen by Sobol and collaborator with the fission track. We do see it as well here, but a bit earlier, around 13 million years ago. We also have this slowing down of the cooling between 11 and 2 million years. And then between 2 million years and present day, we have a very strong cooling event. Now, there's 2 things to note here. The first thing is, with this 2D model, we don't know if the cooling is induced by climate or by tectonics. This is purely the cooling history. And second thing is, if you look at the observed ages versus the predicted ages, we see that the top of the profile is quite well modeled, but the bottom is actually not that great. And this is quite important for us because the bottom of the profile is where potential glacial incision, glacial widening would be happening if we were looking for something. That would be potentially the bottom of the profile, the lower elevation sample that would be affected, the one close to the valley bottom. So to explore that a little bit more, what we did is we went to a 3D model called PCube. And PCube, what PCube does is it allows you to input a DEM and to explore different scenarios of topographic or tectonic with different topographic and tectonic input. So the first thing we did is we tried a steady state topography inversion. So basically we take the present day DEM, and the present day DEM doesn't change from 10 million years to the present day. Here are the results of the inversion. First, we can see that we predict the age. The age prediction is much better compared to the 2D model. So that's really nice to see. And second of all, if we look at the inverted tectonic signal, we again have this 3-step history. So fast uplift rate, slow uplift rate, fast uplift rate. So we can explain or data with a purely tectonic signal, as other studies have done in the past. However, the assumption that you have a steady state topography over 10 million years ago is unrealistic. And yeah, it's completely unrealistic if we think about the fact that the onset of exhumation is 11 million years ago, and we have a strong glacial topography. So what the next thing we did is we looked at the impact of dynamic topography in PCube. And so there's two parameters you can play around in PCube for the topography. There is the amplification, which is basically the relief. So amplification of one means that the relief is the present day DEM, and amplification 0.1 means you have a very flat landscape. You can even go above, but we don't think that's quite realistic. You can go amplification 2, but unless you have a good reason to, that's not something we explored. The second parameter that can control the evolution of the topography is the offset, and that's basically to account for elevation changes, so surface uplift. So what we did next is we fixed, for the new inversion, we fixed the end of the model. So the present day DEM is fixed for the present day. But then we let the model, the inversion, choose the starting stage of the topography and its evolution between the start and the end. And so that's the result of the inversion, accounting for changes in topography. So again, we see that we can reproduce our ages very well. But we can also see that the tectonic uplift rates are completely different. We don't have a strong uplift signal at the start, and we are also completely missing this very strong uplift signal around that started around 2 million years ago in the steady state topography. What we do have, however, are now the changes over time of the topography, so accounting for the amplitude and the offset. So if we look at that and we can look at that and look at what it means for the DEM. Well, so we start with a relatively flat surface at 10 million years ago that gets uplifted up until 1.4 plus or minus 1.4 million years. So I'm going to say it gets uplifted around anywhere between 0 to 3 million years. And then this relatively low relief surface goes through a very fast landscape incision phase to go back to end up as the present day topography. And so this is quite a dramatic landscape evolution. And so we have to ask, is there any argument that would support this topography evolution? Well, there's quite a few. So as I mentioned previously, there is the study by Oskin and Burbank in the Kyrgyz range, who shows that the glacial incision in the middle of the range, so exactly where Ala Archa is roughly of 1.5 kilometers. So that would fit very nicely with our incision signal. Now for the timing of the incision, we also have a stratigraphy section in the Chu Basin, so the sedimentary accumulation just north of the range, where Bullen and colleague in 2001 collected a lot of data, and they saw two things. First of all, they saw a very strong change in grain size deposition around 2.5 million years. So something's happening where you suddenly start to deposit much coarser grain size. And this change is also correlated with a change in the detrital fission track. And the way to interpret that is basically that during those two time periods, a lot of erosion had to happen to remove a lot of rocks. So we do have a big change in erosion dynamics happening anywhere between 3 to 2 million years. That's recorded in the Chu Basin. And finally, if we look at a potential climatic forcing on these changes, well, we know that the onset of glaciation in Central Asia is probably a bit earlier than in the rest of the world. And the onset of glaciation might have happened as early as 3.3 million years ago in Central Asia. And this is derived from a study in Kazakhstan, really close to where we are. I think it's 200 kilometers, 300 kilometers from Ala-Archa. So it's basically, it's very local to the Ala-Archa site. So we feel quite strongly that the topographic evolution that is shown here is probably something that is close to the reality. And what does it mean? Well, it means that it has a very strong impact on how we interpret the uplift and the tectonic input, because if we don't look at the topography, then we have this big increase in uplift rate. If we look at how topography can change over time, then we completely lose this big tectonic recent tectonic event. And that has a lot of interpretation, for any young helium ages in the Tian that are classically interpreted as renewed tectonic uplift, where they might be actually, in some cases, climatic signal and not purely tectonic. All right, so we were here in the Kyrgyz range, and now we're going to go to another place in the Tian Shan, quite far away from the Kyrgyz range, and that's going to be the Anichek Valley. So we were in the northern Tian Shan. We're going to go to the south of the Tian Shan now, and we are in this huge glacial valley that spans roughly 30 kilometers and is 1 kilometer wide. So it's a really strong glacial morphology. And so again, we went and we sampled for apatite helium. And same as the Ala-Archa study, we went where there was a lot of background fission track data already available, because this is really good for constraining the background cooling history that the helium might not be sensible to. And so we have our ages, the apatite helium ages in bright colors here. So again, we have very young ages, anywhere between 2 to 7 million years. And we have here in light blue, we have the fission track from the literature, who's a bit older, so from 10 to 22 million years. And so we basically did the same thing as in Ala-Archa. The first thing we did was to look at the 2D model to really make sure that we had a common cooling history in our helium samples. So that's the cooling history of the helium samples. And we see that we have, again, a really nicely constrained history. So with 2 cooling phases. So the first one that with quite a strong cooling from 30 to, let's say, 12 to 2, very little cooling, and then a big cooling event from 2 to 0. So the predicted age are matching quite well the observed age. But again, we don't really know if this cooling history, what's the part of the tectonic versus what's the part of the climate. So again, we go back to P-cube, and those are really preliminary results. But I think it does show a very good trend. So this is the result for the steady state topography. So the DEM stays the same over time. What we can see here is that our helium ages are not, they're not bad. It's okay. The fission track is not great. Like we lose a little bit of the old fission track. And not we lose, but it's hard to model the old fission track. But it's not terrible. And for this model, we have a very fast uplift rate that drops down around 15 million years ago, and then pick back up again around 3 million years ago. Now for the changes in topography, so where the DEM is allowed to change over time, well, we have the tectonic signal is again different. What is quite interesting is that the old tectonic forcing is actually a bit similar, right? It's not as fast, but it's still quite fast. The timing is very similar. The timing is not constrained by us at all. That's something that P-cube inverts for. And we do have a little bit of an increase of the tectonic signal, but not as much as in the steady state topography. And now looking at how the topography evolves over time, where we do have a very strong incision signal starting at 1.6 million years, so a little bit, maybe a little bit earlier than what we saw in Al-Archa. And so if we look at those topography variable and then we put that into the DEM, here's what it looks like. So we start the inversion at 30,000 years, 30 million years, sorry. Again, that's inverted 4 by p cube. We don't constrain it. And we're not as flat as Al-Archa. We already have some relief, and we already have some, we already have some relief. And then from 30 to 1.6 million years, we have some relief increase, but not that much. We also have some surface uplift. And what happens really between 1.6 and the present day is really again, the incision of the landscape where when the landscape really carves out those valleys. So those are preliminary, but the model ages are quite strong. We will have to explore a lot more variables, and there's other data that we will add to make sure that we are considering any possibility for the topography evolution. So as a whole, if we look at the impact of glaciation on the Tian-Shan, well, if we start with Al-Archa, we have an incision of the topography anywhere between 3 to 0 million years ago. And this incision of the topography can fully offset the tectonic uplift signal. In Enyushek, we have an incision of topography also between 3 to 0 million years ago. And this incision can partially offset the tectonic uplift, but not completely. And as a bonus, Ling Xiao Gong, who did her PhD in Potsdam and is now a postdoc at North Carolina State University, has a paper on the review in geology where she worked in Barskun, which is another heavily glaciated valley in the Tian-Shan. And she also sees a strong incision of the topography between 2 and 0 million years ago. So what does it mean? Well, we are in completely different part of the Tian-Shan. We have widely different tectonic setting. For Al-Archa, the exhumation is relatively recent, only 11 million years ago. Enyushek, it's much older, roughly around 20. So completely different tectonic setting, but we have a consistent impact of glaciation on the topography. All right. So to sum up a little bit everything I talked about. So glaciation do not force denudation linearly. The barium 10 records from the VAR show that you have strong erosion only when a glacial threshold is crossed. And this glacial threshold will depend on the climate, but also on the local topography. Glacial forcing can dominate multi-year landscape evolution. So in the Tian-Shan, low temperature thermochronology and 3D modeling shows that you can have a deep glacial incision of average 1 kilometer over the last 3 million years in heavily glaciated settings, and that ignoring topographic evolution can bias tectonic interpretation when young, low temperature ages that reflect climate driving incision are interpreted as renewed tectonic uplift. All right, thank you.
All right. Thank you so much for the fantastic talk. If anyone in the audience, oh, you're getting lots of little clapping emojis. I don't know if you see those too.
I don't, but
Yeah. Yeah, thank you so much for the talk. If anyone in the audience has questions, you can just go ahead and put them in the chat and we will read them out. Um, in the meantime, I have a question about your first project,
yeah.
with the caveat that I have no background in glaciology or paleoclimate for that matter. You mentioned that you're able to use like oxygen isotopes from sediment cores to like model the spatial extent of the glaciers. How do you go from point to to area for that?
Um, Point area. Uh, well, okay. So can I anyway? Okay, let me find the slide again. Okay. So you have the oxygen data in foraminifera, right? In the sediment core. And so we interpret those variation in oxygen data as variation of sea surface temperature. And those sea, so of course you're in the sea, you're not on land, but if you know the lapse rate, which is basically how much temperature can change with elevation, you can get, so that's what we did. So um, we have the local, we know the current sea surface temperature and we know the current oxygen data. And for the LGM, we basically average out the oxygen data for the LGM. And we also know that we have a local lapse rate of roughly 6 um, degrees per kilometer. So basically, for every data point, we used the DEM, and we said, okay, you have a cooling compared to today of whatever value it is that the oxygen tells you it is. So, for example, for the LGM, the cooling between the present day and the LGM is roughly minus 9.5. And so if you have a cooling of 9.5, that's what it means for the ice, basically.
Oh, okay.
Yeah. And so we did that for every data point we had beryllium 10.
Oh,
So each
cool.
each data
Okay.
point has its own oxygen data attached to it. And then yeah.
Okay. Thank you. Thank you so much. I also wanted to say I thought all of your graphics explaining the different geochron methods you used were fantastic.
Thank you.
Okay, we have a question in the chat. Trevor Faulkner
Yeah.
asks, how do erosion rates vary for one,
Yeah.
sedimentary, and two, metamorphic limestone?
That is a very good question, and that is the blind spot of the beryllium 10. Because beryllium 10 is only produced, well, not only, but we measure it in quartz. So limestone, you're going to be blind to what's happening in the limestone. So here in the map, you can see you have some red. Whoops. Am I still? Yeah, I'm still showing. Okay. You have some red marks here, and that tells you where the quartz-bearing rocks are. And so anything that's not red, you have no idea what the denudation is. But for us, actually, it's not a bad thing because we are looking at the glacial erosion rate. And the glacial erosion rate, where the glacier are, matches really nicely where the quartz is. So I can, with this data set, I have a pretty good idea of what's going on denudation-wise. Anywhere there's in the high part of the catchment, in the glaciated catchment, I have very little idea of what's going on in the low, yeah, downstream, basically. So that's a little bit of the blind spot of this method.
Leaving a bit more time for people to write their questions, I would love to go back to the Tian Shan. You showed
Yep.
us this. I think I forgot. It was around probably after you introduced the first site in
Okay. Yeah.
in the trial. You showed us this map with all of the, I
Yes.
think,
Yeah. Yeah.
AFD or apatite helium ages for the Tian Shan.
Yes.
Yes, exactly. So I was so this is really really cool, the way you brought us to this point, thinking of, okay, this might be also partly a glacial signal here. Is there any correlation between the localities of these young ages and maybe the ELA position as it varies across the Tian Shan, or any sort of climatic gradient or topographic gradient around the mountain that would not be tectonic?
That's a really good question. So those young ages, so that's the yellow one, are mostly on the margin, so either the southern margin of the Tian or the northern margin of the Tian. And that is because that's also where you mostly have the last tectonic shortening is happening there. So for example, the Pamir, which is over here, we know we have a very strong tectonic signal. There's no disputing that. For the correlation with any climatic signal, I do not know. I actually have no idea. I think, yeah, I don't know. That's a good question.
Okay, so it's just I had done some work in the northeast Tian Shan, so
Yeah.
it was the Zhonggar Basin, and there we have high peaks, but it's pretty arid, so it's only about the upper half of the mountains that are glaciated, and I see that like it looks in terms of the AFTH quite different from the
Yes.
obviously more glaciated western part of the Tian Shan. So that was just an observation that piqued my interest there.
No, absolutely. Yeah. And this might be also part of the reason why the paleo denudation rate in the Jenga Basin might not see any or very limited impact of the glaciation on the denudation rate, because if you are in a very arid system compared to the rest of the Tian Shan, you might have a limited impact of glaciation, at least of the erosive dynamic of glaciation.
Fantastic. And maybe just before just to make sure that I'm a bit in a jet lag haze, when you were talking about the QT, was I
Yeah.
the only person seeing a chimpanzee on the screen?
Yes. Yeah. Okay. So
Or
this is
was it in
something.
my head or was it in
No,
the
no, no. That is the symbol for the software.
Okay,
I'm
good,
not sure
good,
why.
good.
I'm not
Just
sure
making
why.
sure that yeah, good. I'm with you.
Yeah.
Good. Grace, you want to take the next question?
Yeah, sure. We have a question in the chat from Luo. You emphasize that glacial erosion efficiency is highly dependent on thermal regime and ice dynamics. Given that your cores span a significant period or significant span a period of significant warming, how do you disentangle the effects of thermally driven ice acceleration from potential changes in the dominant erosion mechanism, e.g., a shift from abrasion to quarrying, in your observed erosion rate signal?
Okay, that's a really good question. So, yeah, the glacial erosion happens in with very different dynamics. What I will say is that looking at sediment core, we are mostly constrained by the grain size. So, and again, those sediment core are great for barium 10 because they have fine sand. But you have a bias with granulometry. So if there is different glacial processes who are producing different grain size, we might miss something. And I think I didn't go that deep into the ice flow model because I'm not a modeler, but I'm sure with the really nice climatic constraint that we have here, if somebody wanted to have a look at how different glacial processes changes over time, I'm sure there is potential for something. Yeah. And yeah, also, I will say that if you're looking at very short changes in erosion, you might be a bit stuck because barium 10 in here has a short integration time, but still, this is not instant. So what can I show? All right, here. So for example, here, so you have the uncertainty in the y-axis, and in the x-axis, this box represent the integration time. And so what you can see is the faster your erosion rate, the smaller your integration time. But when you go into quite low erosion rate, denudation rate, you increase your integration time. So if there is any variation happening, over 2,000-3,000 years ago, you average everything out. So you won't be able to differentiate what's going on really.
You can stay on this slide because I think this is what Martin Margold was asking. So a question from Martin Margold, thanking you for the nice talk. Why was the MIS4 erosion signal in the Var catchment so subdued? Numerical glacial models indicate relatively strong glaciation at that time.
Yes. Yes, I'm changing because I have a slide for that actually.
Okay.
Yeah, actually, that's a very good point. The climatic signal during the coldest MIS5 and the LGM is basically the same, right? We have basically the same oxygen values. What is going to change though is the time spent at this cold period. So this is the evolution of it's basically the percentage of the quartz being covered by ice. So you see that during MIS4, sorry, you are almost at the level at the LGM. But again, glacial erosion doesn't happen in a flash, right? You need, especially with beryllium, you need time to erode the rock to get rid of the previous concentration that was in the rock. And once this is eroded, you export sediment with a concentration that is basically zero. So, and this is where you can get your barium-10 glacial signal. So if you don't spend enough time eroding the rock, you basically, you don't have, you might miss this signal with barium-10. And this is a point that when I say that the threshold is dependent on the topography, that is exactly what I mean, because in some of the catchment, the cooling of the MIS5, 4, sorry, and the topography of the catchment means that you have highs that can stay a bit longer than what we see in the VAR. So every catchment, every range is going to have a threshold, and in here it just means that MIS5 was not cold enough for sufficient period of time to erode significantly the topography.
Okay, thank you very much. So here on this map, the highest point of the catchment, so we have the quartz-bearing rocks
Yeah.
in red,
Yes.
but the extent of the quartz-bearing rocks, okay, so they're being covered by the
Exactly.
vast extent. Okay, yeah.
Yeah. So
That's it.